All right, sweet. We live. All right, sweet. So, you can go and start a new project in Visual Studio or whatever platform you use for your C slash C++
Right.
programming. I have a bunch of pre-written functions in here, and we'll just be looking at the code in each one and talking about what it does. I do have some default imports. For the most part, standard IO and standard lib and strings, which is not on here, will be the ones that you probably will need if you're going to be following along. All right.
Okay.
So just to do a quick refresh, let's talk about variables real quick. Normal variables, not pointer variables, just normal variables. We have these variables right here, normal variables that you can store directly data into them. And they have a certain amount of memory they take up. So this is printing out all the different sizes in memory that all these different variables take. And then down here is the mins and max values you can put in these variables. Just a quick refresher. Now, from our previous class, we just talked about storing data in here. But there in C is a lot more you can do. And specifically, it's in regards to pointers. Because the big thing about C is its ability to be extremely efficient because it's such a low-level language, and that's what pointers allow you to do. Other languages, most programming languages that are used don't allow for any type of pointer manipulation, and some of them allow for very small optimizations with pointers, but for the most part, they're very heavy data-wise. But C applications, this is the greatest improvement they have over normal ones. So let's kind of go over here some pointer variables. Basically, everything that we've seen so far is, this one. Everything we've seen so far can also be a pointer. And there's a new thing that we can do called a void pointer, which is void of any type. It's just data that exists, and it's unknown what the data type is. It's just data. And it's assuming that you, the developer, will know what to do with this data. Because with data types that you imply, the data will be structured in a certain way, bitwise, to take advantage of the format. But when it's not, when it's a void, it's just dumped there. Now, you can print the value of pointers using %p, and you have to do this ampersand thing. We'll talk about that here in a second. You'll see the only difference is we can add these asterisks. These asterisks dictate that we want to just make a pointer. And now if we print this, I think these ones got mixed up real quick. Let's change that around. So we print this, we'll get a different output than normal, because before we would get maybe the value of the variable, but this time instead we get these weird random numbers. Why are we getting these weird random numbers? Well, we got to talk about memory first. And this is where C, really takes advantage and shows its low levelness. So memory itself, people will call it RAM. Let me pull up a picture here real quick. Memory. Here we go. Images. Here we go. We have memory. Let me go to this image specifically. And memory, typically when people think of it, it's going to be like your RAM. You get new RAM sticks. They're awesome. They allow you to do a lot of stuff very quickly, and that's also where all of your running applications are currently. Now, when you ask for a variable, which is some data, it needs to be put somewhere in RAM, in your memory. But how do you know, or how does the computer know to go out and retrieve that data and exactly where in memory? It uses addresses. It uses addresses to find the exact location in memory where that data is. So that's what a pointer does. A pointer is simply pointing to where some type of data exists. It's just basically a bookmark. Think of it as a bookmark for bookmarking a page, just some type of reference to get you somewhere where then you can get the data that you want. So also in memory, we'll be seeing more examples of it here in a second. It's split up into two distinct parts. There are several other parts, but we're not going to get into them right now. We're going to talk specifically about the stack and the heap. The stack is where all of your default variables that you define in your code are stored. So if we go here, all of these guys, all are going to be stored on the stack. When your application is first compiled, the compiler will know exactly how much memory all of these guys need to take, and the stack is pretty much static. In the sense of its layout will remain exactly the same upon program start and won't really change too much. Your stack can't really grow once your application is loaded into memory. The heap, though, on the other hand, is dynamic. The heap grows and shrinks throughout your application based off of dynamic memory allocation that you perform in your application. You'll see examples here soon on how to access heap memory, because everything here that we're doing right now and in C101 has been dealing with stack memory only. And you can see that this stuff is pretty close to each other in memory. It is literally right next to each other, one after the other. This is because they're all on the stack, and it's combined and put together as closely as possible to save on space, but also to be faster because it's logically right next to each other. Any questions on that before we move on? All right, let's see an example here real quick of pointers with normal variables. So right here, we have a normal variable, a normal integer, and we're putting the number 10 in it. We're going to print out the value of that, so we'll see 10, but we're also going to see the pointer value of it, or the memory address of where it lives on the stack. So if we run this, and of course it's going to be buggy, there we go. If we run this, you'll see we're getting the value of 10. And we can also get the value of the bookmark, essentially, of where this data lives in memory, which is this guy right here. And this also incorporates into your OS size. Particularly, you might hear of things like 32 or 64-bit. Those are in reference to how large the pointers are, essentially, for your operating system. How much bookmarks can you have in your OS? 32-bit was limited to, I believe, max 4 gigabytes of RAM max. It was 4 or 8. I believe it was 4, though. That's literally the most you could ever have in your computer was 4, period. Like, that's unusable. So they migrated to 64-bit, which now has a new cap at, I don't know, I think it's in the terabytes range. But now this address space allows you to have up to a terabyte of memory space that you can now use, which should last for quite a long time before OSs will then have to inevitably upgrade to 128-bit based. So you can double check this by seeing that this will be 8 bits long. So if we go ahead and do a printf here. Sorry, 8 bytes long. We'll go ahead and print a ZU, and we'll do size of ampersand my int. We'll go over the ampersand here in a second. So let's go and rerun this, and it's probably going to glitch out. Run it again. So you'll see an 8 gets pointed here. So size of, again, will tell us the size of that variable. So this is 8 bytes long. 8 bytes is 64 bits. That is because we're on a 64-bit operating system right now, and this pointer is 64 bits long. Now, why does this have a pointer? Because this is not a pointer variable. All static variables have a pointer that's the original reference to that variable in memory space. When you have a pointer variable, technically there are two pointers. One is to the original place it lives on the stack, and the second is the value it holds, which is a pointer, which is another pointer to data. So instead of having the number 10 in your variable, you have a memory address instead that the variable is holding. When you run your variable normally like this, you will always get the value out of that memory space. So if that value in that memory space is 10, you will get 10 out of it. If this is a pointer variable and you're storing pointer data, when you run it like this, you will get pointer data out of it. But if you do ampersand, that will work for both. Ampersand is the original bookmarked place where this lives on the stack. The original reference lives on the stack. This is probably the most important thing to understand, or else you'll easily get confused when we go down the pointer loophole here next, is ampersand is the original location on the stack. All right, any questions there before we move on? All right, let's go to the next. So pointers are great for space saving. It's one of the main reasons why they're used. And so let's take a look how we can take an advantage of that space saving. So we have an integer here with the value 10 inside of it. We also have another pointer here to an integer. So some type of integer value we're going to be pointing to. It currently has nothing set to it. So below here, we set the value of this bookmarked location to what this pointer is. So if we now print this out, we're going to see that we get 10 printed out twice. So let's go through this print part here real quick. We get 10 printed here twice at the top. And if we look here, we're printing out the integer, which is 10. And here, slightly different formatting. We have this asterisk, because I told you before that when you do your variables like this and try to print them out or anything like that, this is the value that's currently in that variable right now, which is a bookmark. Because like I said, there's two bookmarks now. There's the original bookmark that lives in there, which you can get from the ampersand, and then there's the bookmark it's storing to go to data elsewhere. So here's the second bookmark. To get the data out of the second bookmark, you can use the asterisk. The asterisk will get the actual data from the second bookmark out. So that is why we include the asterisk here. This is getting the data out. Now you can visually see this on the next two lines here of our print statement. Both of these are exactly the same value. These are the exact same space in memory. Now if we look in here, you can see we're getting the pointer to this data. We're using that ampersand. We're getting the original bookmarked memory location for this data. But for this variable, we're not saying this, because this is holding the value of that bookmark. So to show that it's literally pointing at the exact same location in your memory, You can see it visually right here. So that's how you know that both of these guys are the exact same 10 value. And to do one more confirmation, if we want, right here, we can say my pointer int plus plus. But we can't just do that because, like I said before, this is the bookmark. We can't add one to the bookmark. We need to add one to the value inside of the bookmark. So to do that, bam, we put the asterisk in it because we want to extract the value out of that pointer. So now, once we do this, let me close this and rerun. You'll see that my stuff is all messed up, but that's okay. Let's just do, I think we have to do it like this. Oops, come on. There we go. So now you can see both values have changed. Even though I only changed one variable, I added one to this guy right here, it is a pointer to the other value. They are both looking at the exact same thing in memory. So if it ever changes at all, both of them will see something different because we'll see the change because they're both looking at the exact same thing. They aren't two different 11 integer values copied twice. It is one original integer value in memory, but you have different windows essentially looking at it. Any questions with that? All right, let's move on to the next thing. Hopefully you guys are getting this because the difficulty is going to ramp up and the confusion is going to ramp up very, very quickly here. All right, array magic. People love arrays, and they don't quite understand how they work under the hood. So let's talk about that a little bit. Particularly, arrays are epic because they are pretty much a one-for-one lookup. What does that mean? You don't search through an array to find an exact value if you want the second value. If you want the second value, you directly get the second value from memory. But how is that possible? Using memory magic. So if we run this real quick, and we'll look against the code here, we get 110 printed twice here. And if we look at these guys, 110 is the second value in here. So since arrays start counting at 0, it's 0, 1, so this is going to be in the 1th place. This should look familiar to anyone with past programming experience. If we want to get the 1th item out of the array, we can format it like this. This is telling us we want the 1th item. This, though, might look a little weird. This is to show off that an array is doing some magic under the hood. So if we go back to our stack example, and this goes for the heap too if you were to add an array to the heap, the stack will lay out variables right beside each other, one after the other, as tightly as it can. Specifically, arrays will always force it, so every consecutive piece of memory is a part of the original data set. So what arrays are actually doing in memory space is they're allocating all of this data right after each other, right next to each other in memory space. And when you ask for an item down the chain, it will just add a value to move the bookmark down a little bit so it can directly access the data in that memory spot, because you can predict where in memory the next piece of data is going to be. So that's what we're doing right here, is we're going to the next item in the list. So this might not look like a pointer, but it is. Whenever you have an array, it is a pointer to data. So this is a pointer, and we're moving down the line one value, and we're storing that new pointer here in second. And again, this is storing a bookmark. So to get the data out of the bookmark, we need to do the asterisk. And if we look here, in our memory address, you'll see it's slightly different. It varies a little bit because this is where the first item in that array is stored. And this is where the second item in that array is stored in memory. And as you can see, they're right next to each other consecutively. The variation is because of the allocation for an integer. Because an integer is a known allocation for the OS. In this example, it's the 4 bytes. So 4 bytes you move, or we can do the math here. So 8 is the starting point of the first integer value in here. So 8, 9, A, B, C. C is the start of the next. So we go C and so forth. And that's how we get the data extracted out of memory for these guys. Any questions on this? All right. Let's move on to lists of lists. Now, lists of lists. So having lists inside of lists. This is a very common thing in programming that you will have happen a lot. But this is where beginners typically will start running into their first initial issues. Because you are forced to deal with pointers, whether you like them or not. And it's usually a very hard concept at first for people to kind of grasp and understand. But once they do, you know, it's like riding a bike. Like, you never forget about it, and you just always know how to do it after that. So let's go ahead and run this code and see what happens in here. So start with this. This means we're going to have an array, and doing it again means we're going to have an array inside of the array. Now, this means we don't know how long the first array is going to be. It's going to infer it based off how many items we have in here. But the second one, we specify exactly how long these strings are going to be. Each one of these guys are going to take up 16 bytes of memory in memory in that stack. No matter how long or how short they are, they will always take up exactly 16 bytes. So when we run this, we now know, we can tell exactly how large this item is going to take in memory, and it's predictive on how we can move down it. So just like before, it's a one-for-one operation because you just add to the memory space to, the bookmark, essentially, the pointer, and you can just move down and get the items out of the list. If we were to run this without specifying an item, this is not good practice, but you'll see by default we're pointing to the first item in memory. So that will print out onto the screen. And now if we look at the next item, this will be for the size of the entire array. So if we look at here, it's 48 bytes. So if we look here, 16 times 3 is going to be 48 bytes. So this is pretty on point right here. There is no way in C to get how long an array is though. So you have to use math because C is very low level. You're predefining these things beforehand, so you need to know yourself how long these items are because the computer doesn't know. It's just storing data literally right next to each other. So we know that our entire array is 48 bytes, but we don't know exactly how many items. Let's say you're a new programmer and you didn't see this guy right here at all. How do you figure out, and I just tell you that each string is going to be 16 bytes long. How do you figure out how long the list is? Well, you just got told that each item in the array is 16 bytes long, and you can confirm it by getting the size of a single item in the array. So like I said, this not best practice, but this will point you to the first item in the array. And to get the value out of that, we can use the asterisk at the beginning to get the actual value instead of the bookmark size. And it tells us that it is 16 in size. So based off that information, we know each item is 16 and the whole thing is 48 long. We can do some complicated math here of division. So the total length of everything divided by the size of individual items, and it will tell us that we have 3 items in our array. Now, something that you may want to do also is print every one of these strings. Now, you could go through and print each one by doing like my list 1 and then my list 2 and so forth and so forth. But that's terribly inefficient, especially if you have a lot of data in here, or maybe you're printing an entire file that you read onto the screen. So it's best to put in a for loop, and this is where this stuff comes relevant that I was talking about before, about how you can calculate how large your array is. So if we look in here, we got a basic for loop starting from 0, and it's going to keep going until it hits the size of the array. And we're calculating right here the size of the array, which we did before. And then we are going to print out each item in the array. And you can see we get every single item in the array printed out. So when you deal with lists of lists, again, this is all being stored on the stack. We're about to enter Heapville here real soon, but you're going to have to already start incorporating and understanding pointers at this level right here, just simply having an array of arrays. And this works for any array of arrays, whether it's integers or not. Any questions there before we move on? So let's move on to the heap, shall we? This is dynamic memory, dynamic allocation, where you can be a little smarter. Because the awesome thing about before is, if we want an array, we just tell it how much memory to take up and we make an array and it's awesome, we're done with. But programs aren't one and done. They're dynamic. You're taking in user input. You're reading in files. You're maybe communicating over the internet. Things are changing, and you can't just statically define everything prior. Well, you can, but it might be very expensive memory-wise, because C is all about being very clean, efficient, and as much as you can optimize in any aspect, specifically memory. This arguably is inefficient. Why? Because every single item is being allocated with 16 bytes of memory. Even though these ones aren't taking up 16 bytes, they are allocated for 16 bytes and they are taking up 16 bytes of memory. So we could be more efficient than that. This example obviously is very small, so it wouldn't really matter. But if you have, let's say, a very large file, that's going to be a lot of extra memory. And additionally, there's an unknown factor. How long is a line? You don't know how long a line is. So you're going to inevitably run into issues when you do it this way, because you just don't know. When you're reading a file, a single line could be 10,000 characters long. Are you going to allocate 10,000 for potentially, infinite times downwards? That's going to be a lot more data than if you do just exactly how much each line is. So that's what dynamic allocation can allow us to do. So let's take a look at mallocing. There are two methods that we're going to look at, mallocing and callocating. We're going to start with mallocing because it's the most common one that you'll typically see, but I don't quite recommend it, and you'll see exactly why. Typically, it's mostly for a security risk. So if we run this guy right here, and let me rerun this. any of you security people out there will appreciate malloc. And if you don't appreciate it right now, you'll appreciate it more once I show off this the messiness of malloc. I call it dirty malloc. So if we look at our output, right now we're getting 5, and we're printing out 2 memory addresses. You'll also be able to tell from these memory addresses that this looks pretty similar to the rest of the ones that we've been printing. But this one, the address is way, way different. We'll see why here in a second. So let's look in here. All right, we're making a integer variable with no value in it. And now we're doing something weird here. We have a pointer, and we're running malloc here. What is malloc? Malloc is a way to allocate memory for a variable after compiling it. Because like I said, when you first compile your program, your application will see exactly how many variables you are making. And it will then store that information in your binary, and when you run and execute, it will take up the exact amount of memory in stack it needs to in order to run your application. No less, no more. Well, what if you want an array that is changing in size, or people are appending values to it, or just a variety of different things? That's where the heap comes into play. Heap is for your dynamic memory that can be accessed and given to you at any time you just request it. So what we're doing here with malloc is we're requesting some memory in the heap somewhere. We don't know where. It's not going to be nicely laid out. If we ask and use malloc 10 times in a row, we're not guaranteed to have all of those malloc memory spaces right next to each other like it is in the stack. They could be all over the place. Doesn't matter. So we need to also tell it exactly how much memory we want to ask for, request basically, for our application. So for malloc, you only pass one parameter, and that's the size. The size of the data that you want, and it's going to be in bytes. So this is where size of becomes very, very useful, because if you are making a variable here, maybe you can just do the size of that variable, and then you'll get exactly this size that you need. Or if you want, we can see that we're doing a integer pointer, and you could say integer pointer in here, or you can manually just say the value that we want. And since this is a pointer, a bookmark, and we're on a 64-bit system, all pointers will be 8 bytes in size. So we could do that also. But it's best to kind of keep it like this, especially if you want to be able to be compatible with 32-bit systems, or potentially ARM systems if you're trying to write for that, or if for some reason 128-bit operating systems came out tomorrow, now your code's compatible with it. The less hard-coded values you have, the better for the longevity of your application. So let's see here. Malloc also by default will be returning a void pointer. Void pointer means that it got this data for you in memory, and it's going to give it to you. Doesn't know what you want to do with this or the format the data should be laid out in. It just has the data for you, and it's giving it to you. Now, in literally everything else except for VS Code that I've ever messed with, you can just do this. Because the void pointer by default will conform to whatever variable that you're assigning it to. But in VS Code, it yells and whines and wants you to do a cast first. So this is called casting. Casting is essentially forcing a type on a different type of data. So the format is right before 2 parentheses, and then you can say what type of data you want to be. In this case, we want it to be a integer pointer. So we also have this guy right here. Not required, but also required. So if you don't have it, your application will warn you and yell at you and not really be happy, but it will still let you run your application. But you 100% want it. Why? Because malloc and calloc, so both of them, are a nice request to your operating system. You are literally kindly asking your underlying operating system, whether it's Windows or it's Linux, if you can please have some memory in the heap to use. The operating system can tell you to literally fuck off if they want. And if they do that, you're going to get null returned to you. And if you get null returned to you and you keep running your application, you're going to probably crash because you're not handling when you aren't able to get memory. This can run into lots and lots of issues, lots of unexpected crashing and pain. So simply do a check afterwards if you actually got memory given to you or not. You can do some custom logic here if you want to keep asking the OS if you can get memory over and over again until you actually successfully do. Totally up to you on what logic you want to do, but make sure you do checking. The thing with C is you have to follow the ABCs. It's a luxury that you, in other languages, you don't have to, and you'll be pretty much fine a lot of the times. But in C, you have to do the ABCs. ABCs are always be checking. You always have to be checking to make sure you have data, you have the correct data, it's in the format you want. If you don't, you will open yourself to either crashes, bugs, or exploits, typically exploits. Anytime your application can crash is usually a flag to an exploiter that it's exploitable because you're not handling something correctly. So if we move downward, we have asked for memory on the heap, and it's giving us a bookmark to where that memory is on the heap. We're storing that bookmark here in this pointer. Now again, if you want to get that data out of the bookmark, you have to use the asterisk. So we use the asterisk in order to put this data, the number 5, into the actual data part of the heap, not replacing the pointer or the bookmark itself. So once we do that, we print out the value, which is this guy right here, again with the asterisk so we can extract the value. After that though, we're printing the pointer value that we got from malloc. And then after that, we're printing the bookmark of the stack variable itself. So like I said, there are 2 bookmarks with pointers, and if we look here, you can see we have 2 pointers and they are vastly different in their memory space because the stack always starts at the top of memory space or close to it and moves downwards as it fills up, and the heap starts at the bottom of memory space and moves upwards as it starts filling up. Additionally, it's a nicety because your program with normal stack variables will automatically clear them, get rid of them, and free up memory so you can continue moving forward. But malloc variables, not controlled at all. You're in charge of it. You asked for it. You need to now do the cleanup yourself. So you have to run free afterwards. Free is a special function that will free up the memory from your program and make that memory space now available to other applications. If you don't do this, you'll run into issues where your application is hogging all the memory for while it's running. We've all seen applications like this. For example, Chrome. Chrome isn't because they aren't freeing properly, but Chrome is a good example of being a memory hog because they're just asking and asking for memory, and now they're taking away from what other applications can use. It's a community. You gotta kind of think of the OS as a community where every application is kind of living in this space, in this little town essentially, and you have to ask for resources that you can temporarily use, and once you're done, you need to be a nice citizen and clean up after you're done and give it back to the community. If you don't do that, the community will get mad at you and things on the person's OS will go very bad. To give an example of this, there is tracking for memory leaks in Visual Studio. This is very light tracking, but essentially if you add this guy right here and include standard lib and this debugging library, you'll get access to this function here for dump memory leaks. So when you run your application now, let me close this guy, and just to do a quick reference, we are no longer freeing this guy. So we're not cleaning up after ourselves. So if we run this guy now, it will run normally, but we're not cleaning up after ourselves, which means that in here, I think I have to do this. Why are you not printing out? There we go. There we go. It's on this little output log here. Very hard for you guys to see, but right here it says that there was a memory leak and it was at this address space and it was 8 bytes long. So we didn't clean up 8 bytes of memory. We were being messy. And we were hogging memory that potentially could take a while for the OS to clean up itself. And that's because we did this guy right here. We have a pointer and it's pointing to data and it's 8 bytes long, and there we go. So this will tell you any memory leaks you have so you can go through and clean them up. If we rerun this again without the memory leaks, you'll see down here nothing prints, and that's how we know we have no memory leaks in our application. Go and press enter, look down here, and now nothing prints down here. We have no memory leaks. We're all good and tidy. If you're using Linux and GCC, you can use an application called Valgrind, which I like a lot more than everything with VS Studio. I hate VS Studio, but Valgrind will do analysis on your application to let you know if you have memory leaks, but not only that, it will also let you know how much space in memory your application is taking. All right, any questions on malloking? Oh, I guess one last thing for malloking on why you shouldn't use malloking. You should use calloc instead. Why is malloc bad? Malloc will reach out and grab some data, some memory for you in memory space. But it grabs it just raw. It says, oh, this memory, it's yours. That memory, though, might not be zeroed out. What does that mean? Well, if we run this now and we don't assign a value of 5 to it, can you run, please? You'll see that we're getting this weird output here now. Why are we getting this weird output? It's because there is reminiscent or leftover data in this memory space that we just requested. Now, this potentially could lead to exploits if you have your application in some way set up where you do printing of malloc memory space without any assignment. If you do that, people can now look through your memory essentially and get printouts and see data they're not supposed to, potentially, because there is no cleaning up or formatting of that data before you're actually given it. So it's best to use calloc, because calloc, when you request memory, will clean it and zero it out. And you'll see here in a second when we run calloc. Any questions on that before we move on to callocing? Drink some water. All right. This should look very similar to what we just looked at because it's exactly the same, except we're using calloc instead this time. Let's go and stop this. And rerun this. Now, calloc, instead of malloc, it takes two variables that you need to pass through. The first one is the count, so how many items are you going to be asking for? And the second is the size. How this works in the behind the scenes is just multiplication. So don't overthink it. You can swap both of these values around and it will work just fine because it's just multiplying this first value times the second value to figure out how much data you need to take up. And we just need to take up this much data. So we're just going to do that, multiplied 1 because that's just going to be the original size. So calc though, as you can see, we have it commented out here for our variable assignment. And by default, calc will zero out memory space. So you'll start with clean, new memory with no junk in it at all, and you know it's going to be good. So you can avoid potential exploits or other weird things happening in your application because you know you're starting with nice, clean data. And everything else is exactly the same. Just printing out the value, the 2 pointers that you have, and freeing of that memory. You need to free your memory that is from the heap. And you also still need to do your check. Any questions on that? And just to show, if we remove that and rerun it, we'll have 5 in there. All right. No questions on calcing. Let's talk about strings a little bit. Particularly, this was pretty much covered in 101, so we're not going to spend too much time here, but it's mostly going to be posing the question. You have an application that you're making. Maybe it's a new Epic game or software application for reading files and maybe doing some machine learning or whatever whatever you're passionate about. You need to collect someone's first name and last name. So you just put a static item in here, 8, and now they can enter in their first and last name. Awesome. That works. I can go in here and I can go in and put a first name and a last name and I'll get the printout. Don't worry about the formatting issues. But what happens if someone has a longer name than that? Or a longer last name? You're going to run into issues because this is limited on how much you can take. You can only take 8. So what do you do instead? Do you hard code a larger value in here? Well, now you're taking up more memory. Maybe this doesn't really matter because maybe it's a video game and you're only taking their name once, but if you're storing in a database or a central server, like that starts getting expensive real quick. So that's where calcing and mallocing can come in hand. Or if you had an address book application on a computer or on a mobile device because you're making a mobile app, having this type of setup potentially leads you to allocating a lot more memory than you need and taking up more memory and being inefficient. So instead you can use calc and malloc. Any questions on that?
I do have a question. It's kind of irrelevant to the subject itself, but it has to do with strings
Yeah,
and
what's up?
size. So, I remember that like C-style strings have like a null terminator, right?
Yes.
Does that add up to like the size itself? So like if we had a string with 8 bytes, it would go up to 9 bytes. Would that pose a problem to the code itself? I haven't tested it and I can't now because I'm like at 100% usage.
Yeah, you're good. So this, when you ask for a string, your null byte is included in this, which means that you can only store 7 characters.
Oh, I see, okay.
So
Thanks.
if we run this guy right now and do 1, 2, 3, 4, 5, 6, 7, 8 and press enter, you'll see, because it's kind of glitchy, but this first variable is only storing up to 7. Because the null byte is the 8th, and you can't, if you need more, then you need to add more memory. So that's the weird thing about strings is you need to always do a +1 after your string length. Does that answer your question?
Yeah, thank you very much.
Yep. So that was a good thing to bring in because that's something that you need to incorporate if you're doing dynamic allocation of data. So here's another example of what we did before here, but instead being potentially more efficient. So instead, we're only going to allocate one large block of static memory. Now, you can do more optimizations to this and make a buffer, but at the end of the day, you're always going to have to allow for a certain X amount of input given. So in this case, we're going to do 128. So they can give us up to 128 for any type of input they give us. Now, might seem a little overkill for this small example, but you gotta kind of think of this more at scale when you're taking lots of data from anywhere, from files, whatever. So our buffer here is going to be where data gets temporarily stored when the user gives us something. And these guys are going to be our heap requested data sources, where we only ask for the exact amount of memory space we need in heap to store the first name and last name. So we're being more efficient. So if we look at this real quick, let me go and stop this guy. And let me make sure this is saved. Okay. So we're first going to ask for a first name, and we're going to get the first name using fgets. You can use whatever method you want. We're just going to be using fgets here. So next, you're going to see that we're going to put this data inside of first name. But first, we need to ask for some memory space in the heap. So I'm using malloc here because I made this example before I did the calloc stuff, and I thought I was going to maybe go through it before calloc, but we're going over it after calloc. So you would want to do calloc instead, but we're using malloc. We could just change it to a malloc right now by putting a calloc there. Instead of doing the multiplication here, we'll just do a comma, because like I said, both of these values are going to be multiplied against each other inside the calloc function. So we're saying that for first name, it's going to be a string of characters, and each one of those characters are going to be 1 char long, aka 1 byte, because the size of char is 1 byte. And we're going to need enough memory for the length of the string that's currently in the buffer. So we need all of that. Traditionally, you may also need a +1 right here, because the +1 is going to be for your null terminator. So we're going to need the, well, we can just keep it here. It shouldn't mess with it below. I didn't have it here before because we had some extras padding from the new line character, but we'll just add in here for the visual of it. You're going to typically need a +1 to include your null byte. So after that, we're going to need to do our check again because we're asking for memory from the heap. So once we've confirmed we got that memory, we're going to print on the screen the amount of space that the buffer, the string length that the buffer currently has. So we can see how much memory we're essentially going to be taking up. Next, we're going to use string copy or stern copy specifically, because stern copy is more secure than string copy because you have to specify exactly how much data is going to be copied over. It helps with exploit prevention. Use stern copy whenever you can. So first we need to say the destination. So we're going to be copying data into first name, and first name is going to be a max size of string length, now technically string length +1. That's the max size of string length currently right now. Next is going to be the source of the data, which is buffer, because we're getting the data from the buffer that got filled up with the user's input. And then after that is the max amount of data we're going to be copying from the buffer into first name, which is going to be the size of the buffer -1, so we can get rid of the return character. That's why we're getting the weird printout on the last one. It looks a lot pretty complicated, but I promise you it's not, and this is like the only way you can pretty much do it. And it's pretty much the exact same code for the last name. So we're getting the last name and we're putting it into the buffer. Then we're asking for data for the last name. We're malloking some data, and we can change this to a calloc to be the exact size of the data that we need from the last name. And we'll go and put the +1 here for the null byte terminator. And now we have the return, just in case, doing our checking. And then again, we're transferring the data from the buffer into last name. And then we're doing some printouts here, and we're freeing up our memory afterwards because we got to clean up after ourselves. So let's go and run this and see what's exactly getting outputted here. So first, it's going to ask for our first name. So we'll go ahead and put in a first name. And formatting is all weird, but right here is a 7 because it sees that our string length is 7 characters long. Like I said before, it's incorporating the new line or the new line. So basically your enter. So this is 6 long, and it's 1 more for the enter. That's why we have the -1 right here to get rid of it. So now we need to do a last name. We'll do a last name and press enter, and we'll see here that it gets printed out right here, nice and perfectly, nicely formatted, and it's taking up the exact size in memory that we need, which is going to be 6 bytes and 6 bytes. Well, technically it's 7 because string length only tells you the length of the string and not the null termination at the end. This 7 tells us the length of the buffer string length, which is including the new line character. So an issue comes up, and this is why I brought up earlier the calculation of how large something is in an array, or it takes up in memory. Because when you malloc things, you also lose something. You gain the ability to ask for memory and dynamically grow your memory space and do more stuff than you typically would be capable of. But you lose a lot of tracking functionality. What do I mean by that? Size of. Size of will no longer work properly with calloc memory spaces. You are responsible for tracking how large your memory space is, what this original ask in memory space is. You are responsible for it. For example, if we go in here and we do size of on last name, and we got another one here on, let's do it again here on first name. We rerun this. You'll see that we'll do 1 character here, so that should only be 1 byte of memory, right? And we'll do 9 here, so that should be, well, technically with the null byte, that should be 2 bytes in memory, and this should be 10 bytes in memory, right? The 2 got printed here, and if we press enter, there we go. We got 10 there, but this only says 8. What is going on here? Why does it only say 8? Because size of will always get either this, we'll get the size of the pointer essentially. There's no real easy way for you to get the size of the data, even if you were to do something like this. So let's go ahead and run it like this. And let's go ahead and do 1, and we'll do 3 here. And you'll see now it says 1 instead. To get a better example, let's go ahead and rerun this one more time so you don't get confused with the 2 1s. And you'll still see it says 1, only 1. This is where the confusion comes in, because you are now responsible for keeping track of how long something is when you calloc it. So you will typically see in other C applications, every time they calloc or malloc something, you'll see some type of tracker variable, something to tell you the size of what you calloced essentially, because you have to. There is no other way around it. You have to keep track of how large your stuff is in another variable. Any questions with that? That is why also here in our string copies, we can't do size of last name or string length of last name, because string length of last name right now, it's all nulled out. So it would be 0. And size of will just give us the wrong info. That's why we're doing string length on the buffer, which will be pretty much, it should be pretty much the exact same logic as your original calc, which we changed to +1, but it's fine if this is less than this, as long as this is not more than what we actually did. Any questions on this? All right, this is where the brain hurting starts with that, and then moving forward. So let's talk about calcing lists of lists. So let's go to this function. So here's something new. 2 asterisks. Yes, 2. You can pretty much have infinite amount of asterisks at the beginning of this as you want, and it will always be making, essentially, it will be wanting a pointer that looks at a pointer, 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 and so forth. Why is this useful? For lists of lists. Because this is the same thing as this. They just look different. If I only had one of these, that's the same. It's equivalent to this. That is equivalent to char my list in an array like this. And an array like this, again, is equivalent to that. Any questions there before we move on? Because that's a big point to kind of keep in mind and understand before we move forward, because we're going through a lot of these concepts very quickly. All right. So let's move forward. I have here our tracker. My list size. Well, this is the same name as this, so most likely, if we're reading through this code for the first time, we can apply that some type of malloking or calloking is going to go on, and this is going to be the size tracker. Right now the size is 3. And it looks right here like we got a buffer for some input, so we should expect to get some user's input. So let's look down here. So we're doing a calloc for a char pointer. And we're doing the typecasting here because we need to first allocate the top layer of our array, essentially. So right here is my list size, so it's a 3. So we're going to allocate 3 memory spaces, essentially 3 pointers. We need 3 pieces of data that will be pointers to point to arrays, because we have an array which is a pointer. An array points to more data. So pointer. Do our check, and then in our for loop here, we're going to keep looping for the size of the list, because we're going to fill up the list, all 3 parts of the list, with data. So we're going to get some input from the user, store it temporarily in the buffer. Then for whatever item in the list we're currently on, we're going to calloc some data, because like I said, this is just a pointer when you're doing the, well, in this case, since it's a double, this is just a reference to another pointer somewhere. We're getting and allocating data for the string length. Again, there's not a +1 here because it is taking in the new line, but you can do the +1. We're doing our memory check. Then we're doing our string copy, and we're copying it into that memory space we just allocated. Why do we not do the asterisk right here? Because this function is specifically asking for if we hover over it, well, it doesn't want to show it right now, but oh, there we go. It's specifically asking for a pointer value, not the data value itself, because this function will write in that memory space the data for us, and we'll see more examples of that here in a second. So it will get all of the input from the user, store it in our dynamic array here, and then we'll print it out on the screen. So we look here, we can enter a thing, we can enter more things, then we can enter another thing. And we get the printout of all three items that we have here. Awesome. And it's perfectly memory efficient. Let's see this visually. If you have the debugger open inside of, what do you call this? Visual Studio, so you'll see here there's an issue right now. We're not freeing the memory at all. So we're running into an issue because we have a memory leak now. But that's done on purpose because if we freed it, it would not show up in our tracker here. So if I click this little camera guy here and we look at the memory analysis, you're going to see that we have some memory in here that was allocated, some char pointers. So one here is going to be a pointer to an array. And if we look in here, we can see how much memory it's taking up. And then the other one is going to be a char array, which there's 3 of them. So these are the actual pieces of data that we wrote. And if you look in here, these are the 3 strings that we entered right here. These guys right here. This is them and how much space they take in memory. The first one, and it starts from the bottom and goes up. So the first one is taking up 8. So if we count here, 1, 2, 3, 4, 5, 6, 7, plus the null terminator, that's 8. So we are allocating the exact amount of data we need in putting it in memory. The next one says it's 36. I'm just going to believe it. And the next one is 8 because these lines are exactly the same plus the null terminator. We are being as efficient as possible with our memory allocation, and here is proof of it. The only issue right now is we're not freeing. So let's go over an example of how we would free all this memory. You could simply do a free, and then we need to free my list. But you can't just do that. That will not free all the children. You have to go through 1, 2, and 3. Now, if we write that all out, that's going to be a lot of code, a lot of typing, and we might as well just use a for loop at that point. So let's go ahead and copy one of our for loops here. And make sure this is going to go over the size of our list. We'll go ahead and copy this guy in here. Paste this, change this to an I. Perfect. We're freeing every single child item. But we have one more calc we need to take into account for. After we free all the children item, we need to free the actual the pointer that we first calc'd here. So to do that, we'll just put one more free right here, and we'll remove this guy here. You gotta do it in this order. If you do this first, you're gonna be screwed because this memory will no longer be accessible and you'll throw an error. So if I run this right now, if VS Code will even let me run it, you'll see an error will be thrown and will probably crash. So let's do this. And it threw an error. It's yelling at us, exception thrown right here, access violation reading location. Because this memory is no longer accessible because we threw away all of the bookmark essentially to this data. So now we're trying to access values that don't exist, and it gets just really bad really quick. So order of operations on your freeing is extremely, extremely important. So if we run it this way now, we'll be good. It will not yell and will perfectly clear out all of our memory afterwards once we're done. And we have a perfectly efficient application that cleans up after itself with no memory leaks. Any questions on that? All right. Let's see some usefulness with the pointers, shall we? Because we've seen examples of pointers. We've seen how to use pointers. We've kind of seen that copy, the string copy function. It's doing something with pointers. Where is it? I think I shrunk it. Right here. It's doing something with pointers, this guy. It's doing something with pointers, but I'm not quite sure. It's not quite clear to me yet why pointers are so important or so useful. Like, I get they store, in the heap, where you can put memory in the heap, but like, still don't really get the usefulness. Well, let's show another example of why they're so useful, particularly when it comes to functions. So let's take a look at this function here. Gracias. We got my cool function, and just to show off that this is a function, that's all it's going to do is it's going to say I ran. So let's go ahead and run this guy. And it ran. We're also going to go over just real quick, since in 101 we didn't go over functions at all. Functions are pieces of code that you can run that are separated from everything else. And at the very beginning, they have a type. Void means nothing. You're not going to return anything. You're not going to give anything back. What does returning mean? Literally means giving back. You tell me to go cut down a tree, so I go cut down a tree. But you didn't tell me to give you the wood or anything like that. So I'm not giving you anything back. I might take that wood for myself. Who knows? But you didn't ask for anything in return. So I'm not going to give you anything in return after doing whatever task that you gave me. If you want something in return, though, you can specify any of the variable types, and then you are required to have this return here. In void, you do not have to have the return, but if you do have the return, you just return with nothing after it except for the semicolon. If you are asking for something to be given in return, you must give it in return. You're not allowed to break the law. If you tell me to go to the bank and withdraw some money for you and then give you the money, I can't just withdraw the money and go on a hitchhike across the country and take the money with me. You are not allowed to do anything illegal, period, in your code. You have to return. You have to give the money back. So we have a special secret math algorithm that we're running, where someone is going to give us a number. So this is us telling them that we need a number and it needs to be an integer value. And we're going to return back that number plus itself. So let's go and see that in action. Very, very secret algorithm right there. So when you return something, though, so far you've seen me running these functions. I've just been running them like this, and that's it. That's good. At the end of the day, we just run it and we're done. When someone is returning something to you, like again with the bank example, you asked me to go get you some money. I went and got your money, and I'm giving it to you. This is how you can get that money back or get that result back. When it returns, it will output it, and you can then use the assignment operator just like you would do with like equals to 5 to put it inside of your variable. And to pass data, we're going to put it here. So if we run this, we should see 5 plus 5, so we should see 10 be outputted if I actually undid this guy here. So if we look at this, we're getting 10. Awesome. Perfect. What does this have to do with pointers? We've been talking about pointers this whole time. This looks like normal numbers, normal math. You're right. This is normal numbers. This is normal math. For most people, in any programming language they use, this is going to look like the normal flow. You have data that you pass in. That data is then executed on, and you do some type of return. But in C, you have access to pointers and special sauce and to help with memory reduction and doing things in a smart and intuitive way, not just memory hog. So the issue with this, and it doesn't mean don't use this. Use this when it is fit. The issue though is you are allocating data in memory for this number. Then you're passing this number here. You are allocating memory for the variable here again. So you're double allocating memory space for this guy and for this guy again, because this is an exact identical clone to the original data that you passed in. It is not the original data. It is a cloned piece of that data that you're then performing some type of operation on and then returning. To really clarify that it is a clone, we're going to say, we're going to do our logic instead of right here. We're going to do our logic right here, and we're just going to put an equal sign and remove this. And can't forget about those nice semicolons. So if I rerun this, we'll get the exact same output of 10. And to show furthermore, we are definitely not messing with this original mynum right here. We're going to print mynum right here. So let's go ahead and close this, rerun. mynum is still 5 and the return value is 10. Like I said, exact clone. This could be inefficient, or maybe it's just not as a luxurious feel as what you want with your functions. This is where pointers come into play and can help you be efficient, but potentially make a more luxurious function that is capable of more functionality than normal. So we made our special secret math algorithm 1, and we now learned about pointers, and we want to make version 2 of it, Mach 2. So let's check this guy out a little bit. So let's comment our previous stuff here. Now, we're starting with the same base. My number is equal to 5, and result is completely blank, so it's going to be 0. I would print my result, but I can, here, let me do my result is equal to 0, so that way we don't run into an error with this print statement. All right, so what's going on here though? We're doing some weirdness. We're doing ampersand my num. Well, if you remember before what we talked about, that's the bookmark. That's a pointer to where this data lives. So we're passing through the bookmark to where this data is. Now if we look at our function here for our Mach 2, so number 2, slightly different logic going on here. We're not returning anything at all. So what's going on here? Instead of doing a number and allocating this number space and more data, we're just asking for the pointer to some type of data. Once we ask for the pointer of some type of data, this is not an exact copy. This is literally the original data. This is pointing to, this is the bookmark to the original data in memory. So now that we have the original data, we can perform functions on the original data. And again, asterisk outside of the original declaration is to get the actual data in the memory space. So we're getting the actual data in the number space, which is the number 5, and we're adding it to itself in the actual data space, which is happening right here. So now we have no return at all. We aren't cloning the variable, which we're saving memory space. And now if we run this, you'll see that if it would not glitch out, my num is now equal to 10. Before it stayed at 5 because it was being cloned, but now this function actually altered my variable in its original memory space. And result is still 0 because we didn't return anything and we didn't store it in result either. So it should still be at 0. So you don't need to malloc in order to do memory manipulation and cool things. with pointers, you can do it on normal stack items. And this is how stuff like string copy or string copy works. Can I go to one that doesn't have as much crap on it? All right, whatever. So that's how stuff like string copy works. I'm going to indent it now so we have it a little isolated. Is you're passing a pointer to an array, for first name. And inside the function itself, since it has the bookmark to that data, it's taking the liberty to fill up the data space as liberally as it wants. And that is also why you need to tell it its upper and lower bounds right here with the data sizes, because it doesn't know how large this data is or what type of data it is. It just knows you want to move data from this guy into this guy, and it is doing a clone from this data. It's cloning the data in here into this memory space. That's why there is no return, because it's storing it directly into the memory space. Are there any questions with that? So that's pretty much the majority of stuff I had here written up, mostly just focusing on pointers, static space, dynamic space, the heap and the stack, and pointers, and all the things you can do with pointers and how they can easily get confusing. And then going over a couple real world examples, like this and the other functions up here for like dynamic strings, on how they can be very useful and help you potentially save on memory space and so forth. Does anyone have any questions right now? I did have on the list for us to potentially go into data structures like structs, linked lists, and graphs, which I'm okay with going to the top of the hour if you guys want to get an intro to those. If not, we can call it good. Is everyone satisfied to end it right here, or do you guys want to keep moving forward? I'm going to take that as we are good. Oh, Susanna's typing. What's Susanna going to say?